So what's really behind the glass? So we're going to go through the underlying structure of G8 glass flight instruments at a level that I think introduces the topics and hopefully gives everybody a little bit better insight into how all of this works, so that you're actually looking and understanding what's behind the glass. My name is Andy Fonnell. I'm a commercial pilot and flight instructor. I provide individualized instruction, first-time students to aircraft owners. Started flying when in gliders when I was 12. And then I work professionally in engineering and product development. I'm a senior adjunct professor at University of St. Thomas here in St. Paul, where I've been teaching for over 15 years, and pleasure to go through this with you. It's a first time putting a presentation like this together, so I look forward to any feedback. I know I've got a lot of inquiries about this topic, so look forward to sharing what I put together for you. First of all, a quick acknowledgement. Thank you, Laura and the FAST team. You are getting Wings credit if you stay, I think it's 50 minutes through this. You can sign up for these recurring webinars. They're awesome every Saturday. She went through that. And then there'll be a recording on this on her YouTube channel. Just look up Saturday Morning Coffee and Wings if you want to look back at this recording. And a quick shout out to a few individuals that helped do some review and give me some approval on some of the images. Charlie over at Aspen, John Lacey's a local pilot, does a lot of volunteer flying, and Samuel over at Garmin Aviation. Thank you for that. This is a follow-on to a previous webinar that looked at the traditional flight instruments. It covered the six-pack under the topic of crack open the six-pack. Looked like that was a pretty popular, well-received presentation. So this one's going to be in the same spirit of understanding what's behind there when you're looking at these instruments and getting a better understanding of how they work. Laura, did you have that poll question put together by chance?
I do have that poll
All
question
right, I'll let you.
right now.
Okay.
Do you feel you understand the workings of glass? And the answers are yes, no, or some. So pretty easy there.
Mm-hmm.
And we'll let those answers come rolling on in. We will end our poll in 5, 4, 3, 2, 1. Here's our results. 36% of us feel that they understand the working of glass flight instruments or electronic flight displays. 17% do not, and 47% have some understanding.
Great, that's glad to see people are learning this stuff already. That's great to see. So the information on electronic flight displays at a real system level is actually pretty limited. If you look at the um, Pilot Handbook of Aeronautical Knowledge, there's literally 4 pages and pretty high level, more about the from a user perspective. So you might argue it's in a way maybe not as necessary, because in these systems the electronics and the systems actually tell you when the instruments aren't working, so they're more intelligent in that way. But it's important, I think, to gain a better understanding because of the susceptibility some of these have, some of the operating considerations that feed into the risks that you want to consider with even with electronic flight instruments. But like the pre-show, if you were listening, the reliability of these are absolutely better than the mechanical instruments, and the capabilities are absolutely amazing. So we'll begin by going through electronics, a breakdown of this topic into some basic understandable elements. Next, we'll look at how the core technologies are applied to the temperature and pitot-static instruments. Then we'll look at similar the information that's provided by traditional gyroscopic instruments and how that's applied, the technology is applied to those. And then some practical considerations that really address some of the risks as a pilot you should take into consideration, especially even for aircraft owners, as you're either upgrading or flying with these type of electronics. So electronics are a broad topic, and for the avionics applications, we've got kind of 3 categories. I kind of grouped them into that we'll go through. The first one is around sensors and transducers, and explain a little bit more about what that is. The second one is a little bit of an overview on the core elements, focusing on like a processor, what's a PCBA, how do they get integrated into modules is what I call them. And then when you have all of this, how are they interconnected? So talking a little bit about communications and how these elements all talk to each other. So I call it a digital world out there. Everybody hears about that. What that means is these glass flight instruments, or formerly called electronic flight displays, EFDs, rely on electronics that are, in the simplest terms, take physical inputs. So think about like temperature, pressure, and they also take user inputs, so buttons that could be on touchscreen, and convert them into digital signals that a processor, in generic terms, there's different types, but a processor in general will then, along with other electronic elements to do the logic functions, be able to display information in a human readable form. So in a little bit graphical form, you have these physical inputs. They come in, they are what we call analog, so they're continuously formed signals. And through some electronics, then they convert that into a digital form, which means in discrete, like zeros and ones, if you will. So the more bits you create, the more the resolution, the better the accuracy. And so electronics over time have really enabled all sorts of processing, both in terms of resolution. Some of these displays are, gorgeous looking in terms of what they can display, and also the amount of information and the accuracy. So you'll see that in a cockpit that's been outfitted. The one above here is from a Bonanza. It's got a complete glass cockpit. You've got your primary flight display, and we'll talk a little bit about that. But you'll also see even down here, like in a Cirrus, there's more than just the primary flight displays that are now electronic, right? We've got engine instrument displays, navigation information. We're going to focus on just the electronic flight display, so the primary flight instruments, but it's a whole world that you've been able to digitize and really bring a lot of information. And that's one of the key enablers of doing this. Process that information and display it in a really compact form. So that's and the capabilities of what you can do with that information, and do everything from like synthetic vision, is what these systems, I think, really bring to the table over just providing the primary information. So the first basic element are sensors. So in their simplest definition, they detect and respond to a physical phenomenon, converting it into a measurable signal. And an example would be like an electrical voltage. It also might just provide a means to measure something. And so these physical phenomenon that we focus on that are important for flight instruments are pressure. So we convert that to an electrical signal. We have temperature, we convert to an electrical signal. Acceleration, that includes gravity. A lot of understanding around these accelerometers and different devices, we'll talk sensors we talk about, rely on gravity, which is an ever-present acceleration that actually is established, and then magnetic field, which we're familiar with from compass use. The signals from a sensor are either whether you drive them with and measure them from what they output, they're usually very small, and they're very susceptible to distortion. And so first thing that usually happens is you need to process it and amplify it. And in the simplest terms, these are the functions that what we call a transducer does. So as I've shown here, you go from a physical input, you've got a sensor that'll create let you measure an electrical signal characteristic, could be resistance or voltage. If you package that with some signals, you can do some conditioning to create a more measurable, usable signal. And that's done with a transducer. You'll see here with electronics, there's so many ways to integrate or partition the boundaries of what you do. And in this case, a very common thing to do is package the sensor elements with some electronics to be able to get a sensor transducer versus just a sensor. But there's examples we'll show of both. Laura, can you do the second poll question for us?
Yes, I can. I just launched that. Are you
Awesome.
familiar with MEMS? Yes, I know a little. I know what it stands for, or no, I've never heard of it. And I have to confess, No, I have never heard of it. So on that, I will end our poll in 5, 4, 3, 2, 1. Here's our results. I see that I am not alone in not knowing what MEMS is because 79% of us have never heard of it. 21% of us do have heard of it, know a little bit about it, at least know what it stands for.
Nice. Good. And there's nothing wrong with that. That's why we're here to learn about this. And it's not memes. So MEMS is what they're called. Click forward here. So MEMS are micro electromechanical systems. The way I describe them as layered 2D sensors. They use semiconductor manufacturing methods to create tiny mechanical moving parts that allow you to convert some of these physical movements into electrical signals. And we'll show how they get applied into our avionics. Semiconductor manufacturing methods are what are used to create what people are more familiar with, like computer chips. So those same processes and industry allow you to create now little movable parts in the same form factor. So we're talking about, and courtesy of Atomica here, their website is down there. You can get the image and see more about them. One of the largest U.S. MEMS fab. A fab is called these manufacturing facilities. These are very small devices and elements that are features that are used to create a MEMS device. And when you compare a sensor that provides a similar functionality to your traditional instrument, you're looking at something that's on the order of 100 times smaller. And now you can begin to appreciate why all of this stuff begins to get packed into such a small little form factor. But these devices, when you look at the traditional flight instruments, right, it's very artsy, crafty, and it's very mechanical and represents some great and interesting and fine engineering, that you imagine like a watchmaker type skill set. But now we're talking about something you can't even see. And these chip wafer manufacturing processes start with in a clean room. There's a whole industry. These are very large fabs. You create these features through different processes of layering materials, etching them. There's specialized processes I won't go into that allow you to create this in a specialized environment, usually a clean room. They're done on a wafer, which is what you see here in this image. And those little squares that you see are now the individual either a sensor or a chip elements. The next thing you have to do is get them off of there. And the way you do that is you actually slice them out. So they have a dicing or a saw machine that allows you, or a cutter that allows you to take individual chips out. So we call that singulation from those wafers. And then you need to then package them, is what it's called, into a form factor that lets you do something with them and interconnect them with other components, electronic devices. So these are packaged devices. You can see the little pads. These little gold looking pads are how you solder or connect into this example component, but there's many different form factors, many different shapes. But these MEMS devices, along with other electronic parts, get put onto a circuit board, which is kind of that green looking base that has all the little wiring interconnections to interconnect everything in the specialized way. These photo examples are all just is essentially random images. They don't represent any relationship to one another, but eventually you can put a housing around this and get yourself a flight instrument or whatever electronic you might have. Same thing, how a smartphone would be made. So just a little bit, it's a lot of words here, but just a little bit of like understanding electronics. The processor, or sometimes you might have multiple processors. It could be a microcontroller, a microprocessor. It could be digital signal processors. But just in general terms, you'll have a processor that takes all these inputs. It takes and signals either from sensors or even from other electronic parts. It performs calculations and creates outputs. And it does that using programmable software. It's embedded software, so we call that firmware. And those other electronic components come along with the processor. They can include resistors, capacitors, memory, other integrated circuits, displays, indicator, lights, power supplies. All this stuff gets integrated onto something, what's called a PCB, a printed circuit board, because it's printed. It's a circuit that interconnects everything. And the way designers interconnect all of this, they have design tools and they create schematics like this or a circuit diagram that connects all the little uh, connection points from all the individual components together. And then they go off and fabricate that. And like as I mentioned, that software that runs all of this is called firmware. And the application software might be something that's actually driving from like your computer. Um, Once you have that, you might package that into an enclosure. You can have connectors connect up to it. You can have cables or wires that give you a little bit of an umbilical length. I call these like a module level. It's just an easier way to think about them. And that allow you to now digitally communicate with everything. So all that electronics processing is happening in there. And this is just an example of a GPS antenna module with an integrated cable. And again, in this case too, these are just unrelated images, but just kind of illustrate the point there. Um, these modules, as they're connected together, there's different ways to do that. That's gone through what's called communication. Um, these are just some examples I just drew of drawing the boundaries in blue of what might be like a module. They connect up into a communications module. Some of these might all be integrated into one big module. Um, if you directly communicate with the main system or in another system, that's one way to communicate. That would be an example of, for instance, like you may have like a printer that you connect directly to your old desktop. But more commonly nowadays are what are called like bus communication, where you have a communication network similar to like your electrical bus, where you gang up uh, items to be able to get power off of a common um, item. In this case, you'll have electronics communicating over a network. So that now introduces the concept of the communications. And if you're going to have multiple devices talking to each other or be able to share a communication link, you need to put some standards around that, especially if you're going to expect components from many manufacturers talking to each other. And in this presentation, I've introduced photos and examples of different products that are out there. There's no endorsement here that's intended. It's just by example, I've tried to pick examples from many different types just to illustrate the concepts. For communication, there are in avionics, there's ones that I've listed here that are fairly common. Um, what you use them for depends on the application and some of the trade-offs between cost, speed, packaging. Packaging meaning how integrated you can implement it. That's typically like an indicator would be like the number of wires that you need to put in place to enable that communication. So I've kind of listed that here. You've got your old RS-232, so you can see it's fairly slow. It's that direct point-to-point communication. It's a lower cost, simpler. But if you want something more advanced, that's on a bus where you can interconnect multiple. You might use SPI, as it's called, serial peripheral interface. I2C, as it's called, RINC. There's many different standards that provide certain implementation requirements to provide, for instance, like error checking or speed. And so there's a lot of options that engineers that are developing these avionics have available to them. Because they're supposed to interconnect modules, there's some standardization that's expected. Some of them are just over the years, but there are industries bodies that help manage and control the protocols, as they're called, about how you implement and communicate over those buses. As a pilot, you'll never be involved in that. If you go work for an avionics company, for instance, you'll get some of the interesting insights. But as a user, you'll see that the way you connect up different modules might rely on some of these different communication protocols. So as an example, this is from an Aspen EFD 1000 E5 system. I mean, if you look at the manual, you'll be able to see some architecture diagrams. This is very typical for electronics. They show these block diagrams of how things are interconnected. Not unique to any one company. It's very common in any type of electronic system. And I just highlighted some examples of how this company has implemented interconnecting some of their peripheral modules. Some are using this I2C. We've got some of the a dual connection for different data transfers. Even now with this latest system, pulling some of the AHRS data off of the primary flight display and feeding that into an autopilot provides using Ethernet, providing a higher speed connection. So a lot of implementation, and you can kind of start to pick out and understand how these things are interconnected, including some of the, working on older legacy, converting those legacy systems. You'll have a converter module. So and then that converter module takes care of being able to talk to the primary, in this case, the primary flight instrument there. So all of this, unlike your traditional flight instruments, right, they're very integrated, standalone. Now you have to connect all of this, and that comes with a lot of wires and cabling. And so this was somebody was selling a used system on eBay. So I thought this was really neat because it showed the cable harness that they had pulled out that would interconnect their primary, I think the second display, including to some of the modules. So it just gives you an idea of every one of these connections requires wires. And remember, depending on the communication link, will determine the number of wires and the speeds. And so each one of these systems, companies, products, they all require interconnection with wires. So a lot more wiring going on is the point. Just schematically, the way to think about starting to see how this is all stitched together. Again, electronics provide a lot of modularity, a lot of flexibility on how you do integration. That's determined by the manufacturers, but it's also somewhat driven by where you want to provide and implement the sensors, right? So the magnetometers or your antenna items like GPS antennas, you'll want them located in more isolated locations that aren't susceptible to some of the aircraft other systems. So we've got, in this case here, temperature, static pressure, ram pressure, the acceleration. This is my display out of the way. We've got the magnetic field, and even in some cases, you'll be able to start to look at, like GPS signals are coming in. That's not one of the primary ones we're looking at, but GPS or satellite input is another example of inputs that are taken and then processed. For the primary flight instruments, again, taking these physical parameters, they have to be converted. So you'll have like a temperature sensor, and I kind of showed it in brown as like the sensor module, sensor element. It'll get packaged into an enclosure, and then it might talk to a communication module, and then you might run the wires up to and we'll talk about a little bit more about what these items are here that go into your air data computer. And then the acceleration allows you to feed into the accelerometers, the gyroscopic sensors that constitute the primary components in an AHRS or attitude and heading reference system. So these, with the magnetometer also going into the AHRS. So these are the two common aircraft module systems that are talked about also in your pilot, the PHAK, the Pilot Handbook of Aeronautical Knowledge, that feed into like primary flight displays. But these are electronics, right? So they're small. And that's the beauty of, again, electronics is you can modularize this. You can make them separate for replaceability, ease of use of that, interoperability with other systems, or you can integrate them. So we'll show us some examples here, but this diagram shows some of the primary elements there. So how does this apply to the first topic, which would be our temperature and pitot-static instruments? Those are the three that are highlighted on the dash, and then also your temperature sensor, which is up there. So in the diagram, I had a similar one in the previous part on traditional instruments. You've got, this is just, again, an example, not meant in any way endorsing, but there's all sorts of PFDs we'll show that might take in your static pressure down here. They'll take in your ram pressure, provide the same functionality as your airspeed indicator, traditional one, your altimeter, your vertical speed indicator, all integrated now into one display. This one has even more navigation information, but the primary instruments are up here in this case. And then for temperature, because you can now locate it in a different location, you can put other sensors, for instance, in this module, it'll be run back to the primary flight display actually through one of those communication links rather than a direct connection. And then the static line, which are tube connections here, go off to, in this case, the transponder as well. A bit about temperature sensors. Didn't cover it last time in the other presentation, but there's a nice article by IOPA you can look up from Thomas Home. Talks a little bit about, these are bimetallic materials. As they change temperature, they change shape. They are directly coupled to the indicator needle, like most mechanical or traditional flight instruments. And so they're all packaged together in one unit. Here's a temperature gauge that you would see in a typical general aviation aircraft. This one I took apart. It's actually coiled, anchored at the bottom in the tube, and then directly connected to the indicator needle. So like all these traditional flight instruments, they're all integrated. So if the temperature needs to be in view to the pilot, it's going to be somewhere, in the cockpit and then sticking out through the either through the cockpit face here or side windows. So these temperature probes are usually very closely located in the cockpit area. With electronics now, the world can change quite a bit. The implementation can change. There's three basic type of electronic type sensors. Thermocouples, just to jump down here, they're based on two dissimilar metals being welded into what we call a bead. That junction creates a voltage essentially through the Seebeck effect, and it's temperature sensitive. These are temperature sensors that are typically used more in industrial applications because they can withstand very extreme temperature ranges. Well beyond what like aircrafts are experiencing. So avionics typically use either RTDs, resistant temperature devices, or thermistors. So RTDs are real simple. They are just a resistor element. So anything like a platinum wire. So in this cases, you have a trace or just a length of, in this case, platinum or material over a long enough length that as temperature changes over the range of interest, you can measure a change in resistance. Now you have an electrical form, you can process it, and you can send that signal and convert it into a displayed reading. So there's electronics that go with this particular sensor element. Semiconductors, again, wafers that you build up semiconductor chips with. You also have materials that are temperature sensitive, and they're kind of listed here. But if you're going to be putting a temperature sensitive element on a chip, you might as well integrate more electronics. And next thing you know, you have temperature transducers in the form factor of something that's the size of your pinky tip, right? So these are images from this is the manufacturer's called Analog Devices. It's 80. The product is our 590. Comes in different form factors, same underlying sensor, and they have some electronics that let you take the temperature, convert it to a voltage, and then run it as a current. So the whole point here, though, is these are very small form factors, and the 8590 is used as the sensing element in some probes that manufacturers use for their temperature gauges that you as an aircraft owner or as part of your installation would have. And that looks like this. So we use outside air temperature, one, to understand what the temperature is outside, especially for like icing concerns. But you also use it now for calculating true airspeed. So you don't have to manually move the dial that's on your traditional airspeed indicator. It all calculates it for you. With electronics now, right? You can now do stuff with those signals using a processor and the firmware that's integrated. And in this case, those temperature signals are usually sent by a communication link to the primary flight display. And here's some examples. This is from a Garmin, researching on the internet about how they've integrated using an RTD probe. This one here uses a communication module and sends that to the primary flight display. So you got a little bit of a link between that and here to package and install it. This is one of an RSM, they call it, from Aspen, that uses the outside air temperature, packages GPS, and also we'll talk about that magnetic flux or heading sensors all in one module then since you're going to be integrating it, puts it out where you get a good reading of all of those physical parameters. So for pressure, there are MEMS devices now applied where we take the pressure and we're building this up on a wafer. So this is zoomed in here of a wafer level. Think of this like a trampoline. So now you've got a sealed little cavity. We're talking super small. And as external pressure is applied, this thin element bends and stretches. And what we need is an ability to measure that deformation as an electrical signal. And so there are little electrical resistor elements put in that translate the stretch of the material to an electrical signal. And so we call those little sensing elements that are integrated as part of that wafer fab. And that's how you get a pressure transducer. We use those to measure RAM, static, subtract those, you can get airspeed. RAM is your total, and they're small. So those chips usually have some kind of fitting over them so that you can slip over the tubing that is coming from your static or your pitot tube. And you can now put this sensor inside your electronics. I'll show you an image. Whereas in the traditional flight instruments, we've got, if you remember, we've got those port connections on the back. They go into that diaphragm or bellows, and then that is mechanically coupled to the indicator needle. So for the traditional flight instruments, you had to have everything integrated in one cylinder or can type enclosure. So those signals, they provide you the airspeed, altitude, temperature are kept together as a module. It's kind of standardized, called the Air Data Computer, ADC. You can always, again, integrate other functionality, but that's the primary function of your ADC. It can be a standalone module like down here. They can be integrated. This is a really cool image that shows from the Aspen where you hook up in the back your tubing from your pitot, your static. And then that's from the user, that's the outside connection. But if you look inside, there's a little, this is just a bulkhead connector that connects the tubing, that connects those connections onto the circuit board on which those MEMS devices, those pressure transducers are mounted. And that's where you can now imagine that entire system is all integrated directly into there. So in this case, your ADC, your air data computer is all integrated right into the flight display. So pretty amazing packaging there. And there's a lot of other examples from other manufacturers. Others provide a little bit more modularity. So there's an example of where you might have these standalone. They could be, like I mentioned, integrated into your flight display, or they might be integrated into the other system that has the gyroscopic elements like your AHRS. We'll talk about that in a minute. So the other instruments that remain are your gyroscopic from again, looking at this traditional. So you got your attitude, your turn and slip or your turn coordinator, and then your heading indicator. And the question is now, how do you convert all of this into electronic flight displays? So these are, we'll talk about the elements, but they are organized in different modules. Again, you can integrate any number of these or keep them separate, but the industry is kind of standardized on putting the main attitude information into what's called an inertial measurement unit, IMU. That has your accelerometers, gyroscopes, and usually magnetometers or processes those inputs if they're separate, like physically located elsewhere. Its job is to provide this data, but it doesn't yet convert it into a usable information to a pilot. So it has enough functionality and responsibility, if you will, that it's organized into a module. It feeds into electronics to be able to display this into useful information of your attitude and heading. That's called your AHRS, so your air data attitude and heading reference system. When it's integrated with an ADC, it's an ADRS, so it's got the air data attitude and reference system. Without it, it's separate, but you can integrate these together now as well. And you can integrate all of these into one module, right? So the flexibility you get with electronics based on the manufacturer's offering can be quite expansive. INSs really don't apply that much, I would say, to general aviation. Um, they're more advanced. They do make some with MEMS, but also even more sophisticated electronic systems that provide higher accuracy than, let's say, MEMS, but they are a system that doesn't rely on outside referencing, a constant, like a zeroing, if you will, or referencing system to be able to know where you're at, and provide a lot of accuracy, especially for like transoceanic or long distance navigation, more so for like airliner or military large aircraft, I would say. So there's some examples you can go find. If you ever want to develop your own system, you can buy an IMU. They're again used a lot. These technologies are also used in unmanned vehicles. You're a lot of that whole world as well. So, and there's like another example down here. You can have different levels of functionality, capability, performance. So there's a lot of options out there from different manufacturers. Just giving a couple of examples, again, not meant as any endorsement. So the building blocks of an IMU really come back down to some of the fundamental elements from MEMS devices. Um, because they're two-dimensional, like I mentioned in the previous slides there, looking at MEMS, you somehow have to take these, what used to be three-dimensional um, gyroscopes or instruments that moved in 3 dimensions, and now you're building something in a layered fashion. So it is 3 dimensional, but you're only able to have something that's like rotating or moving in 2 dimensions. So there's different principles that people relied on to be able to get the same type of, be able to provide the same type of information to a pilot, but breaking down the systems into 3 different elements. So they are an accelerometer. A lot of you have probably heard of those. Um, and they provide information based on acceleration. Gravity is one, so you're always in your seat or because of gravity. It gives orientation acceleration that feeds into providing bank and pitch. You do have gyroscopes, but they're different. They rely on the Coriolis force or Coriolis effect, and we'll look at those in a little bit more detail. They measure angular velocity or angular rotation, so you can get that from each axis, and then through processing together with the accelerometers, you're able to provide pitch, bank, yaw, and then with magnetometers, they rely on Lorentz force, which is related to the Hall effect. We'll look at those, and that gives you heading using the magnetic field from the Earth. So we can get the same roll, pitch, yaw information, but they're based on different sensing elements that, again, rely heavily on MEMS technology. GPS, you'll see, is implemented in many systems, not just for navigation, but you can actually get altitude and position. They're sometimes integrated with your primary flight displays or as an external input. They provide supplemental options, backup options for altitude, but they only do this as like the geometric height above sea level, and it's usually just as a backup informational purpose for that role as altitude. So gyroscopes, before we get into the MEMS, remember they only require air or electric power to operate. So their principles are precession and rigidity in space. And you've always got some kind of spinning rotor that's mounted on gimbals that, depending on the implementation and constraints, give you the information that we're looking for. And I thought some people were interested in the history. You can find through some searching. This is a good website. You can get a little bit more of the overall history, but they are a very old technology. Again, back in obviously in 1800s, nobody had wafers or semiconductor, but so everything was more physically scaled and sized based on what you could build. So looking at those three elements, building blocks of an IMU, we look at accelerometers first. They look at the rate of change of velocity. So if you're moving at a certain velocity constantly, there's no acceleration. But if you change your velocity, that change is what's acceleration. So that's that backward. If you add power, move your throttle forward, you'll get that push back into your seat. That's now you're changing your air speed, so you're accelerating. Or if you pull power back, you're going to decelerate and move forward. Gravity is what's always pulling us down. So we always have this ever-present acceleration pulling us down. And together with multiple accelerometers, usually you implement three, you can process the output of that into bank and pitch information. So I'm not going to, again, this is an introduction to all of this. The intent is not to go through the complex equations that the electronics and firmware we use to calculate all of this. But once you've integrated all of this on a circuit board, it's very easy to do those calculations. So how do these work? It is interesting, though, to understand these MEMS devices at the high level. You've got a fixed item here. It's this inner part in the terms of an accelerometer. I'm showing just one element here. And you've got in MEMS devices, they call these proof masses. It's the movable part. In this case, it's a mass. It can move, in this case, left and right. And you can see like an image here zooming in using like a scan electron microscope. So this stuff is tiny. And they use these little fingers, as I call them, or combs, and you measure the capacitance between those, the rigid part and the movable part. So as you move closer or further apart, you're able to get an electrical signal. You convert that into a relationship with the acceleration, and then you can process that. So sounds complicated, but once you implement it, it provides very powerful information. So you can orient these in different directions. So you can get, this is just again, one illustrative example of like if I'm banking to the left, if I had a MEMS element oriented like this, gravity is going to angle the downward direction to the left, and I'll see some of this move. Depending on the bank angle determines how far this is going to move, because these little arms right here are like springs. So these are tailored to and controlled and related to the amount of spring force. Same thing if I pitch back, I'll see this accelerometer. If I had one, for instance, like this, the proof mass would slide to the back, and depending on how much it slides to the back and deflects these little spring arms will depend how much I'm pitching up, because gravity is going to be pulling this back. So gyroscopes, there are MEMS gyroscopes. They're based on the Coriolis effect. I'm not going to, again, this is not a treatise on the physics and stuff, but just introducing the concept so you kind of understand how the engineers and scientists develop these elements. These are based on vectors. Vectors, when you essentially multiply them or cross them, create the known resultant. And the way this works is, in order to get the information that you need, they create what's called a vibrating structure. So these are called vibrating structure gyroscopes, VSGs. Another name you might see is Coriolis vibrating gyroscopes. There's all sorts out there, right? So once you understand the basics, you, as a company, you might make different versions. But you take that same proof mass, just like you had an accelerometer, they have a proof mass, you vibrate it back and forth. Again, that's done through the electronics. And again, this is two-dimensional now. Remember, all of this is on like a wafer die. And what happens is the Coriolis effect essentially creates a resultant force if you put this moving proof mass in a rotating reference frame, which is the green. So you'll hear, like, remember, there's like Coriolis effects from weather phenomenon. Same concept applied to these chips to be able to create a resulting force, which is what happens with this red frame. So the proof mass is mounted in the red frame, which is mounted into the outer frame that is now rotating. So you get a movement, a resulting movement of the red frame, and that is measured through the same technology of these little fingers or combs. And so you can see something like that implemented at a die level. This is all put on a little package. Again, remember I showed you in that earlier element, you take the die, you put it in a package, and you can now mount this into a circuit board. So incredible level. Again, we looked at earlier, 100 times smaller, the amount of integration and reduction in scale that you're getting from this type of information compared to like those physical gyros that sit in your traditional instruments is what's enabling all of this to get packaged down into something really small. In order to get everything continuous, they implement this as a vibrating structure. So, and there's like if you're really interested, they have these things called like the right-hand rule, so that it's like an easy way to figure out when you cross two vectors, what's the resultant. And so I just kind of added those little images in there. The last one is the magnetometer. So this provides uses the magnetic field of the Earth to be able to provide heading or yaw movement. Um, these are called Lorentz force magnetometers, or LFMs, is a common type. There's some other variations. From my research, this is probably the more common one, or the common one. It's based on the principle. Again, you don't need to like understand the low level physics, but if you have a current carrying element, so you'll have this on the chip, if it's in a magnetic field, it'll cause electrons to move towards one side. That creates a voltage difference across this element that's measurable, and it also creates a movable force called the Lorentz force. So the Hall effect is the measurable voltage, if you will. And there's like Hall effect sensors. There's all sorts of other sensors that leverage these principles. In avionics, we use the Lorentz force because in the chip itself, the movement of these elements is what's measured again with those fingers combed. So there's a right-hand rule again because we're crossing vectors. But if you wanted to, you can find there's different companies that make these magnetometers, and then people that are designing these avionics are buying these components, integrating them with other electronics processors onto circuit boards to create your flight displays. So I found some nice research papers. They kind of illustrate the principles of these MEMS devices, MEMS magnetometers. You've got the magnetic field. Let's say that's going through this chip. You've got the current flow that we talked about. They're on little spring elements. They're driven by a voltage or a current, and then you can measure the capacitance change as these things move, in this case, back and forth through the Lorentz force. So bottom line is we're talking small little measurements, small little forces at the chip level that are then amplified and processed into signals that can be then displayed as information. And all that information is processed through electronics and firmware software. You can buy these little components. Here's an example from ST Microelectronics, a little magnetometer that you can buy. So these things are all sold or available as individual items that are then put together into products. So to recap, electronics and sensors enable integration and of the flight displays. They basically take the traditional temperature, pitot-static gyroscopic instruments and package them into electronic flight displays. The primary instruments are organized into a primary flight display. Like this is the level of information you'll see in the PIAC. And then some of the underlying elements that enable all of this are these MEMS devices and electronic sensors. So I think to me, sensors are a key enabler that the industry and amazing engineers and scientists developed that allow us to integrate all of this. And then people piggybacked off of, the electronics industry. The good news is they've standardized onto modules. You can interconnect them through communication and provide a level of replaceability, or in some cases, you know what, it's better to integrate all of this into one display because you have a smaller aircraft, and that's maybe the primary value that might be offering. So a lot of, again, I can't emphasize enough, electronics allow so much flexibility, so much modularity, so much integration. So that's the overview. I would call like the understanding the level of underlying structure. I think that gives you a good understanding of some of those principles that now define these flight instruments different than the traditional ones, right? So we've got Lorentz force, Coriolis force, acceleration, temperature varying materials that allow you to measure temperature. And then we also have MEMS devices that allow you to measure pressure, right? So really fascinating. And then electronics integrated and then communicate. So these are electronics, and I don't know about you, but you probably hear a lot of concerns. You've experienced some of this, but there are considerations I'm going to go through and give a little bit better understanding of how you can manage these considerations, which basically is a softer term for the risks, right? So operating temperature is one of them. electronic components. Remember, electronics manufacturers are buying these components, and the industry is standardized on operating temperature ranges and also storage. But in terms of operating temperature ranges, they have components that are certified to commercial ranges like 0 to 70, extended commercial, industrial, and even military. And then there's actually like automotive under the hood gets into really extreme hot temperatures. So the industry is kind of have these like standardized groupings. The avionics industry generally picks up industrial temperature rated components. So it doesn't mean that they don't work in hotter or colder, but it's what the manufacturers certify them to, right? Or test them to. Um, so some manufacturers may offer extended ranges. So you might see components from -40 to 125. There's again lots of variations, but these environment temperature ranges are local to the components, right? So it's the surrounding environment of the chip, but at a product level, and product I mean like the avionics itself, they are going to be limited in a more narrow range because you have heat dissipation. We'll talk about that. But if you look around, a lot of avionics are typically rated for -20 to 55 Celsius. So that's the environment outside of the product. And to enable that temperature range, they're selecting most likely components that are rated for a more broader range. Um, One thing I'll go a little bit more into like these commercial components, commercial devices that we bring into the cockpit. These are not certified avionics, but like a lot of people are using tablets, like an iPad mini. If you look at the website, these retail type commercial products are even more limited, right? So the official operating temperature range of an iPad is only 0 to 35 Celsius. So just to keep in mind when you bring in commercial electronics into an environment of avionics, you might end up with a more limited range. Electronics are not to give a treatise on cooling, but just some basics. Electronics have heat dissipation, right? You're using electrical energy to create signals. They always have some inefficiency, and that inefficiency manifests itself as heat dissipation. Um, some of you that, especially if you're flying at higher altitudes, you get quite a bit of solar radiation. If you calculate the typical irradiance from the sun and just multiply by the area, you'll see whatever's exposed to the sun, if you have something on the glare shield, you're talking about like 100, 200 watts of heat being dumped into that just from the sun. There's other things, if you have heat generating components that your nearby devices that could be dumping heat into your electronics. So there's considerations on heating. Cooling is either done by what we call natural or forced convection. Forced is a fan or blower. Natural is just the natural buoyancy density differences that allow you to cool. Um, they make these slap-on tinted shades. You've got your shades on your aircraft, but I actually keep this in my flight bag. I've got a little one that I can slap on if I'm flying and I've got a hot sunny day and the sun is coming directly at me right under, let's say I've got an iPad that's more susceptible to the heat. Definitely look at that. The other way would be cooling. Um, the general equation to think about for cooling, like the amount of cooling you need is proportional to the available surface area and the temperature difference. So if you need to cool down your surface and you've got a hot environment, this temperature difference is going to be small. So in order to get more cooling, you use a fan, and what you're really doing is increasing what they call this heat transfer coefficient. So I won't go more into details, but you've got heat inputs, you've got heat generation, and the trick is to get enough cooling um, to keep things within the operating temperature range. Everything is based on dissipating heat, and dissipating heat means you have temperature differences. It's like a voltage drop. So semiconductor chips themselves that are active, like a computer chip, actually runs at really hot temperatures. So you're usually limiting those, we call those junction or die temperatures are usually up to like 150 Celsius. Just as a point of interest, right? You're not going to feel that on the outside, but when manufacturer designing these avionics, they have a lot of these constraints are taken into consideration. So when they say your outside environment needs to be within this range, it's to make sure that those electronics stay within their operating range. What happens if you go beyond that? I will say it depends. Some of it could be you're just going to shorten the useful life. You're going to degrade it. Others, you could cause a malfunction that could show up as, an error on the boot up or the operation. So there's not like one failure mode when you go to outside the temperature ranges. EMI is the other big one. Um, and what is EMI? So electromagnetic interference, and I put this magnifying glass, it's called EMI because it's like software, you can't see it. And um, there's three types, and I think it's important to understand these basics because you've got a lot of wiring, a lot of electronics, and the cabin is now filled with opportunities for interference, meaning one electronic part may not play nice with another, and then it could start to cause malfunctions or oddities. And for me personally, the one I've experienced is your autopilot. Older traditional autopilots being influenced by advanced electron avionics. So there's radiated, which means this is the stuff that gets put out into the air. So radiated EMI. So these are radio waves essentially, EMI electromagnetic waves. You have conducted, so your radiation, if you will, can go down wires, and it can also couple, right? So you can have a wire going from one point to another. If you pass it close to another wire or another system, it could couple because everything electromagnetic has a field around it. So think of it as like some ways like a force field, but you have a lot of ways of coupling and influencing other things. There's a little diagram you can find that these industry is kind of described, but when you do testing, which is done to make sure that you ensure some level of interoperability, we call that we call that electromagnetic compatibility. And so you have like a source. You're going to measure how much you radiate out. You're going to measure how much you conduct out. So that's your emissions, and you have standards. I've kind of shown an example here. You actually, all the avionics manufacturers sometimes publish a conformance to certain standards. So this is, I call it how much your product spews out into the world. It could be, again, through the air, along wires. And then you also test for immunity. So knowing that every electronic device is going to be spewing out or onto wires or through the air radiation, electromagnetic radiation I'm talking about, you want to make sure that you aren't susceptible to a certain level of it, right? So you test to that. These standards only can do so much, right? You cannot anticipate the interaction of all of these EMI, electromagnetic fields, and what can happen with your electronics. So you have to realize there's always some level of risk. The manufacturers, the more you integrate, the more they're testing their own products, the more you mix and match things, the more potential risk you would have. Because again, there's only so much that you can ensure that you comply with. And interference, if it happens, from my experience, it's unexpected and usually under specific conditions because it's one of these things where when something like a voltage, when a certain level or amplitude, a condition, a pulsing interferes, it may create that's only when it really creates a difficult situation. So long ago, actually quite a long ago, the FAA has recognized the risk. You see it all the time when you're flying in the airlines, right? The old days they used to tell you shut all your cell phones off all the time. Now you can at least use Wi-Fi on board. But if you read the regulations, Part 91, even Part 121, Part 135, there's the same. Actually, it's pretty much the same. You are not allowed to be using this because you're mixing in consumer products with avionics that they were not tested to the same standards. However, there's a get out of free or get out kind of a clause here. This is the 90 the B5, if you will, allows the operator of the aircraft to make the ultimate determination. So you in the general aviation, as the pilot in command, are going to be able to bring whatever you want on board. But I will say, be careful. Some of you may have personal experience with things not playing with your glass cockpit or your old traditional like autopilot's not all of a sudden behaving oddly when you bring devices into the cockpit. And it's for that reason these portable electronic devices are actually regulated. A couple other things. Things are not perfect. I know we're getting close to time here. There's backup considerations and requirements. You can see here in these glass cockpit um, uh, Cirrus and Set 172, but yet you still see these traditional flight instruments. So what's going on? You put all this money into a gorgeous and very capable flight displays and what's required here. And that's the requirements around standby instruments. So over time, you have more proven capability, reliability, but there's been some changes. I'm not an aircraft A&P or not my area of expertise, but just from what I've learned and looked at, you've got Part 23 here that it used to be very prescriptive about what's required by the manufacturers for backups and standbys. Those are very important, and it's transitioned to something broader and basically more performance based. But yet there are some guidance documents, advisory circulars that still refer to what you should follow. So the legacy, there were four independent, if you look up the old 23.1311A5, which if you go to the CFRs, you can go timeline, you can look up all these old legacy ones, actually a very nice interface. Your magnetic indicator, altimeter, airspeed indicator, attitude indicator all need to have backups, but they do allow them to be electronic. So here's an example of a Duchess cockpit that has the traditional as backups. Here's a Bonanza that has electronic as backups. So you can see those where my cursor is right there. And that's within this clause here that specifies how that's allowed. The new standard now eliminated that 1311. It now has the 23.2510 and a number of other ones. But really, the advisory circular remains. You can get this on the website. And the part that's interesting, I find, if you read through this, when you look at some of these cockpits, some of them don't have that. And why is that? So this is an example of a 172 here that has two PFDs, but yet it has no backups, or at least it doesn't seem to. And that's because you are allowed to not have those standby traditional instruments if you have dual ADCs and AHRS instruments, AHRS modules. So by virtue of this individual unit having fully integrated air data computer and AHRS, and you do two of them, either while you might be flying with the PFD here and your MFD here, but the ability to be able to make either one of those PFDs is what allows you to eliminate all those what you would consider standby instruments. And similar with this manufacturer, all sorts of companies provide that where you now have that dual backup capability and don't need to have all those traditional backups. Last, to close out, you can see here, I was doing some work in this is a 340. I've got my little portable device. Those are portable electronic devices. And keep in mind, they don't behave like your primary flight display. They do have some really cool features like synthetic vision, but read up on the manuals and understand what type of sensors they actually include. So some of these, like the one I was showing, has just very basic accelerometers, some GPS. So you'll see not a lot of horsepower in terms of processing capability, even though it can do synthetic vision with your tablet. But also know that if you throw it on the glare shield like that, it's off at an angle. These things don't reboot and zero out. So I, for instance, have it in my checklist to reset the synthetic vision. You can do that. Last, Laura, if you don't mind doing a quick poll check, because I have one slide left to wrap up here.
Not at all. I will launch our question. What type of charts do you fly with? None, paper only, an EFB on your smartphone, an EFB on a tablet, or do you use an EFB and paper? And then I'll end this poll in 5, 4, 3, 2, 1. And here's the result. Couple of us fly with nothing. 12% of us paper only. 5% EFB on smartphone. 51% EFB on a tablet. 31% use both an EFB and paper.
Yeah. Yeah. So a little bit less about the primary flight displays, but with all this electronics, what kind of backup considerations? So there's a nice advisory circular on the use of electronic flight bags, even for training and instructing, really using the state of the art is encouraged now. Um, there's a lot of examples of these electronic flight bags that provide a lot of capability navigation. Um, I've come to an instruction with a student and my tablet battery was dead. So no problem. I actually have a battery backup I keep with me, a battery pack. Um, I've run into where the cables were broken. So when you think about using these electronics, think about how you're going to have your backup plan because all of this stuff is vulnerable to breaking. Less, again, the certified equipment that goes into the dash is a different story that's by regulations. But for your own personal stuff, when you're using these think about, are you going to have a second tablet? You can use your phone. Have you ever tried using your phone as a net, for your navigation? Keep cables. So I keep a little fanny pack for all my electronic backups. It's got two compartments and it lets me keep it up in the cockpit because it's a crowded area usually in small GA planes. And putting your flight bag up there with all this stuff doesn't work. Some of the bigger aircraft, you can't actually reach back to your flight bag. So just my point here is like make sure you give that some considerations. Nothing worse than having something go dead and then the frustration there. So in summary, to get from traditional six packs, it's all about electronics, all about sensors, these modules that integrate all of this with the two of these in different form factors to give you these amazing displays. And then all that software then lets you do stuff with that information, including creating things like synthetic vision, calculating your true airspeed. But keep in mind some of these considerations, operating temperatures, PEDs, interferences, it's good to try everything out in VFR conditions before you go heavy IFR. For instance, if you're going to mix and bring in different electronics, and then make sure a little bit related peripherally is this whole idea of electronic flight bag.